Hello, today we'll look at 4.1 exponential functions. So, I want us to cast our mind back a little bit. When you hear the word exponential, I think your mind goes back to exponent, right? So, if you think about exponent, you've done some work. Some of the key things that you've seen probably in exponent are the laws of exponents. So, if you look at a couple of examples, we said am times an is always am raised to the m plus n. Am divided by a to the n is the same as a to the m, a raised to the m minus n. If you had a raised to the m raised to the n, then we said it was a raised to the m times n. So you have all these rules that you have worked with in the past. But one of the major characteristics of exponent was exponent characteristics are it's got a base raised to a power. And sometimes they call the power exponent too. So the major feature of an exponent is it's got a base and it's got a power. So if that is our feature for an exponent, let's think about what an exponential function is going to be. Remember that a function takes in an input and an output. So let's see how we define an exponential function. So an exponential function is also going to have that same characteristic. It's going to have a base raised to a power. But now as a function, the input is that power changes to become a variable. All right. So for example, in what we have here, you have f of x, and my base is 2, but then the power is no longer a number as you've seen in the past. It's rather a variable that you have, so that when I ask you about f of 1, the input is 1, so it's got the base 2 raised to the power 1, which you'd get 2. And then if I ask for 5, f of 5, that's going to be the same as 2, the base 2 raised to the power 5, which is 2 times 2 times 2 times 2 times 2. That is 2, 4, 8, 16, 32. So another feature of an exponential function, other than having an input resulting in an output, is it grows faster. So as your input becomes bigger, the y value grows really bigger than if you had a linear function or a quadratic function. So because of that feature, we also say that an exponential function grows exponentially. It grows really fast. It grows rapidly fast as x gets bigger. All right. So let's see the examples that they have over here. So clearly you can see that if you start off at f of 30, that number is almost in the trillions. All right. And then if you look at g of 30, if it's a squared, a quadratic function, that's really a small number. So that's one of the things about exponential functions. So you can even imagine about our current situation right now. If you think about the coronavirus that is with us right now, if you look at the number of cases, you can clearly see that the growth of the number of cases being reported is not a linear progression. It's not a quadratic progression, but it kind of feels and looks like an exponential progression. All right. So let's kind of come up with a general formula for an exponential function. So we are going to define an exponential function having a base called a raised to the power x. And we need to be careful. So if f of x is equal to a raised to the x, we got to classify what a should be like. So we are saying that a has to be greater than what? Greater than 0, for the fact that if it's negative, see what's going to happen if you have, let's look over here. If you have negative 2 to the x equal to f of x, then you can see what's happening over here. When x, the input, is even, then I'm looking at positive numbers. But if the x, which is the input, are odd numbers, then you end up getting negative numbers. That is not the characteristic of an exponential function. It's supposed to grow and not be bouncing off from a negative number and odd number. So for that reason, we'll like to make sure that our our base, is always greater than 0. Another condition we want to make is that we don't want a to be 1, because if a is 1, there is no growth, because 1 raised to any power is always going to be 1. So for that reason, we're going to classify our definition for a base, for an exponential function, to be f of x equal to a raised to the x. Bear in mind that a has to be greater than 0 and a cannot be 1. Okay, so let's look at some examples over here. If I have f of 2 and I plug it into the first function, I'm going to get 2 to the 2. If I plug it into the second function, the same 2, the input 2, then I get 3 to the what? 3 to the 2. And then if I do the same, h to the 2, I get 10 raised to the 2. All right. Well, this is no fun, just plugging in input and output, but the real meat, or the real part that you can really enjoy about exponential function, is graphing exponential functions. All right. So let's look at how we graph exponential functions. And I'm just going to use 1 or 2 examples, and let's see what happens. Okay. So if we look at the first graph, let's look at the first function, which is f of x equal to 3 to the x. For now, let's just use some tables of values to kind of figure out what's going on. So if this is my x and this is 3 to the x, which is what f of x is, let's pick up some numbers. Let's pick up negative 2, negative 1, 0, 1, 2, and let's try and figure out what the y values are. So this gives me 3 to the negative 2, which is 1 over 9. Get 3 to the negative 1, which is 1/3. I got 3 to the 0, which is 1. I got 3 raised to the power 1, which is 3. And I got 3 raised to the power 2, which is 9. Now let's attempt to graph this function over here. We can clearly see that if this is 1 and negative 2, this is 1 and 2, we are seeing that this is 1, 2, 3, 4, 5, 6, 7, 8, 9. We are saying that at x equal to 2, that is 9. When x is equal to 1, that is 3. At x equal to 0, that is 1. At x equal to negative 1, that is 1/3. At x equal to negative 2, that is positive 1/9. So right there. So you can clearly see that as I go more negative, I'm getting a fraction that is getting closer and closer and closer to 0. Never crosses it. What do we call that? That's an asymptote. That's a horizontal asymptote. So we can clearly see that there is a horizontal asymptote at y equal to 0. And if I try to plot the curve, it will look like this. and then go this way. And then increase that way. Let's look at another one. Let's look at, say, f of x is equal to the, let's use 5. Yeah, 5 is too big. Well, let's just use 2. 2 raised to the x. All right, so let's create another table. That is x, that's f of x. And let's do -3, -2, -1, 0, 1, 2, 3. So I end up getting 2 to the -3, which is 1/8. 2 to the -2, that is 1/4. 2 to the -1, which is 1/2. 2 to the 0, which is 1. 2 to the 1, which is 2. 2 to the 2, which is 4. And 2 to the 3, which is 8. So I can actually plot this, and let's see what happens. Okay, so if I try to plot this, I get 1, 2, 3, 4, 5, 6, 7, 8. I get my 1, I get my 2, I get my 3, I get my 1, 2, 3, -1, -2, -3, 2, 3. Again, when I start to plot, see what happens. At 3, I'm at 8. At 2, I'm at 4. 1, 2, 3, 4. At 1, I'm at 2. At 0, I'm at 1. And then at -1, I'm at 1/2. At -2, I'm at 1/4. At -3, I'm at 1/8. So again, I'm getting the same kind of curve. It looks like it's cutting through there, cutting through there. And keeps getting closer. But it never crosses that line. That horizontal line, y equals 0. So let's look at the two and kind of come up with some characteristics. So the first thing that jumps to mind is that both of them, it seems like the curve passes through 0, 1. Would that mean that every exponential function is going to do that? Because at any base raised to the power 0, you're going to end up at 1. So at 0, your y value is going to be 1 for every exponential function. That's one of the key things we see. 2, it's got a horizontal asymptote at y equal to 0. 3, the domain is all real numbers. And 4, the range is 0 to positive infinity. All right. Now let's see what happens when I start. So remember that my base is supposed to be anything greater than 0. It cannot be 1. So we can always try any numbers in between that. So let's try and do another example where I am looking at f of x equal to 1/2 raised to the x. Okay. Now let's try and plot this. Well, if I set up my table, x, and this is 1/2 to the x, then if I go with -2, -1, 0, 1, 2, then I get 1/2 to the -2, which is the same as the negative reciprocal is 2 to the 2, which is 4. And then if I have 1/2 to the -1, that changes to become 2 to the 1, which is 2. 1/2 raised to the 0 is going to be 1. and then 1/2 raised to the 1 is 1/2, and 1/2 raised to the 2 is 1/4. So if I try to plot this now, it looks like this. Add negative, let's put out the points out there. That's -1, -2, 1 and 2. I have 1, 2, 3, 4. So add -2, the y value is 4. Add -1, the y value is 2. Add 0, I'm at 1. Add 1, it's at 1/2. At 2, it's at a really small number. So again, see what happened. The curve will pass through 1, keep going, and will never cross the y equal to 0 line. So we have a horizontal asymptote one more time. Y equal to 0. And so it looks like if you have a whole number and not a fraction, let's see what's happening. It looks like if you have a whole number, you are always increasing from left to right. And if you are a fraction, if the base is a fraction, then you are decreasing from left to right. And in both cases, you are passing through the point 0, 1. Okay, so let's go back to the textbook and see what they did. So they did a comparison between 3 to the x and 1/3 to the x, and they have both of the graphs drawn. And one thing that is missing is the textbook, so they didn't put that there. But when you are doing your work, you got to make sure you put your horizontal asymptote right there so that everybody knows that you know that it's not going to cross that line. So one thing I want us to look at is if I took this equation 1/3 raised to the x and I simplified it a little bit, I would get y is equal to 3 to the -x. And if I look at the red curve is 3 raised to the x. It looks like there is some form of transformation going on over here. If I look at the graph of 3 raised to the x, and I perform a transformation, and I hope you figured out what that transformation is. Yes, if you reflect about the y-axis, you end up at the blue curve. All right, so we could have equally, even if you had a fraction, 1/b raised to the x, you can always convert that to b raised to the -x, and all that will be is that the base is now a number bigger than 1. So you see that as the same as the functions that we just worked with. F of x equal to 2 to the x or 3 to the x, and all you are doing is reflecting it about the y-axis. All right, so and just put that down. That goes to this with the transformation of reflecting the graph 3x about the y-axis. All right, in other words, if I had f of x is equal to 1/b to the x, then this is the same as writing this as b to the -x. That is a reflection. So if you're going to do that, you can think about if g of x was Well, never mind. Let me not do that. That might be confusing. But that's what's happening over there. Okay. All right. So let's see some family of functions, exponential functions, see how they behave. So if you look at the right side where I have 10 raised to the x, you can clearly see that as the base gets smaller, you are moving away from the y-axis. You're going to pass through 0, 1, but the smaller your base is, the further away you move from the y-axis. Whereas if you look on the left side of the graph, if you have 1 over 10 as the base, 1 over 5, 1 over 3, 1 over 2, now the smaller the base is, all right, as a fraction, the closer it is to the what? To the y-axis. So if your whole numbers are getting bigger as a base, you are getting closer to the y-axis. If your fractions are really small, they are getting closer to the y-axis. Okay, so you can see how the yellow line, the yellow curve, which is 1 over 10 to the x raised to the x, is closer than 1/2 raised to the x, which is further away from the y-axis. Whereas if you look at 10 raised to the x, that is closer to the y-axis than 2 raised to the x. Okay, all right, so let's see, what is this saying? There are two kinds of exponential functions. Okay, so that's just what I explained out over there. So yeah, they're saying that if the graph is between 0 and 1, you're always going to decrease rapidly. So you decrease from left to right. And then if the base is greater than 1, then the function is going to increase rapidly from left to right. Okay. We can also see that we talked about horizontal asymptote. So as x is getting bigger and bigger than 1, if the base a is greater than 1, then your graph looks like this. All right, passing through that point 0, 1 with the horizontal asymptote right here. And if we talked about horizontal asymptote, so let's see what's happening as x approaches positive infinity. Y is approaching what? Positive infinity. And when x approaches negative infinity, y is approaching what? 0. Likewise, if the base is a in between 0 and 1, then your graph is going to look like this with the horizontal asymptote right there. And again, as x goes to positive infinity, y approaches 0. And when x is going to negative infinity, y approaches positive infinity. Okay? Any questions? No questions? So now, we already talked about range and domain already. So the question is, can we find an equation or the exponential function if I given you just a point on the graph? Can you find some information? So our go-to function, exponential function, is always going to be a raised to the x. We're going to define f of x as the base a raised to the x. So if you look at example 1, if you have the point 2, 25, all that tells us is that the input was 2, the output was 25. So f of 2 is going to be equal to a to the 2 must be equal to what? 25. Now we're going to apply some of your exponential rules over here. So here a squared is equal to 5 squared. So since the powers are the same, it must mean that a was what? A was 5. So your function is going to be 5 raised to the x. If we look at the other example, we have f of x is a to the x. They give us the point 3 comma 1 over 8. Now, this is the 3 is the input and 1 over 8 is the output. So, if I plug that into my function, f of 3 is supposed to be a to the 3, which is equal to 1 over 8. So I'm still going to do the same thing. I'm going to try and match up these this equation to see if there's anything that is common that I can pull out from. So a to the cube, if I brought 8 to the numerator, that's going to be 8 to the negative 1. Well, 8 seems to be something to the power 3. So that is the same as a cubed is equal to 2 raised to the negative what? Negative 3. All right, well, let me rewrite it this way. 8 is the same as 2 to the third raised to the negative 1. And one of the rules of exponents says that I can multiply the powers, so this becomes 2 to the negative 3, a cubed. All right, we're almost there. Well, I need the powers to be the same. So let's swap things around. Let's rewrite this as a cubed is equal to 2 to the negative 1 raised to the third. Now we can see that the powers are the same. A has to be what? 1/2. So I took a really elaborated way to solve this problem. But clearly, you could also see that you could find the cube root of 1 over 8, and you'd also get what? 1/2. So trying to expose you to different things. You could do your rules of exponents and kind of work it out from there, or you could also use your radical expressions to kind of help you simplify the equation that you have. So we are saying that the function f of x is equal to 1/2 raised to the x. And that should match up. If it's a fraction between 0 and 1, the graph should decrease from left to right. And if it's something greater than 1, for example, the 5 raised to the x, then it should increase from left to right. So we are perfectly okay. All right, so the next piece is to look at transformations. Because now that we have this exponential function defined, we can do exactly the things that we did in 330. We can do transformations. And every function that we're going to look at, we should be able to look at the transformations of this function here. So let's look at the very first example that I have. So the first example, it looks like my base function is f of x is equal to 2 to the x. All right. Now, when I add a plus 3 to the power, what does that mean? If you cast your mind back, anytime we did something like this, x plus 3, that was what? That was a movement, a horizontal movement. So you're moving the graph of 2 raised to the x to the what? To the left 3 places. So this becomes 2 x plus 3. So this was shift horizontally to the right, to the left, 3 units. Let's call it 3 units. Let me rewrite this. To the left, 3 units. We know the base graph of this function here. It's got a horizontal asymptote, and then the graph passes through 0, and since the base is bigger than 1, it increases from left to right. So if that is the case, and I'm saying shift this graph 3 places to the what? To the left, the only point that I have here is 0, 1. So when I shift 3 places to the left, the final graph is supposed to look like, I still have my horizontal asymptote. Nothing happened to it. It stays the same, but the point 0, 1 is not going to be at 1, 2, 3. It's going to be right here, -3, 1. And the graph is going to go do something like that. At 0, this point here is 0, 8. All right, so that's a quick transformation. Now let's see if we can figure out the next one. So the next one, my base function is f of x is equal to 3 to the x. And that graph looks like this, passing through 0, 1 with a horizontal asymptote right there. So what does it mean to have 3 to the negative x? So 3 raised to the negative x means that I must have done a negative x, which is a reflection about the what? About the y-axis. Okay, so this is going to be 3 to the negative x. And then what am I doing after that? I'm adding a 2 to the f of x. So I have f of negative x plus 2, which is a shift upwards by 2. So that would mean that I'm now going to get 3 raised to the negative x plus 2. So let's see how the graph looks like. From my base graph, I'm going to reflect about the y-axis. So it's going to look like that. That's my reflection. So this is f of x is equal to 3 to the negative x. And then if I complete the total transformation, if I complete the transformation, I have a horizontal asymptote right here. It says that I'm supposed to raise this graph by 2. So the first thing that changes is that the horizontal asymptote is going to move up 2 places. So I'm going to go 1, 2, and now I have my horizontal asymptote right here. And then the point, which was 0, 1, is going to move up 2 places. So it's not going to be 0, 3. So this is 2, 3. Did I do that right? Yep. So also 1. If you add that, you're right there. So now the curve is supposed to look like that, which is 0, 1, 0, 3. Okay. Let's look at some other transformation, 2 more transformation. So I have this graph here which says 1/2 raised to the x minus 2 minus 3. So my base function is f of x is equal to 1/2, 1/2 raised to the x. And what am I doing? I am taking that and I am moving it to the right 2 places. So I get 1/2 x minus 2. And then I am moving it down 3 places. So I have f of x minus 2 minus 3 is 1/2 minus 3. So I know the base graph of this function here. It's decreasing from left to right, passing through 0, 1 with a horizontal asymptote right there. Okay, so let's plot this. If we plot this, let's see if we can do all in one. This is telling me that I'm gonna shift to the right by 2. So I'm gonna go from 0, 1, and I'm gonna shift to the right by 2. So I'm gonna end up at 2, 1. So I'm at 1, 2. So I'm at 2, 1. And then what am I doing? I am also moving down by 3. So I'll end up at 1, 2, 3. I'm going to be right here, which is going to be 2, -2. All right, so that point moved from there to there, from 0, 1 to 2, 1 with the horizontal shift, and then down with the vertical shift. So that final point is going to be at 2, -2. And then I have a horizontal asymptote that was right here, and that was right here, y equal to what? Y equal to 0. And that's going to go down to what? Down to 3. So now I have a new horizontal asymptote at 3. So this is 1, 2, and that is 3. So I get a new one. And so I can sketch the graph now. At 0, you just got to figure out where the y-intercept is. So at 0, what do I have? I have 1/2 to the -2 minus 3. This is the same as 2 raised to the 2 minus 3, which is 4 minus 3, which is 1. So my graph should be doing this, going through here, going through there, and going through there. All right, so that's it for me. Hopefully this was something that you found entertaining. And in my next video, we'll look at a simple application of exponential functions. Okay, thank you.